Okay, in this tutorial we're going to look at calculating potential and potential energy when we have a spherical source of charge or a point source. So we're going to move from the simpler uniform field that we introduced to the more complicated non-uniform field that's still fairly symmetric, so a little easier to deal with than a non-symmetric, non-uniform field. Okay, we'll introduce two equations. They are in your reference tables. These equations are fairly straightforward, but they look remarkably similar to other equations we have. So you got to be really, really careful not to make silly mistakes. I'll do a few problems here, and then we'll practice in class. So come in with any questions, as always. All right, so I'm going to give you the calculus version of it. You don't have to understand this, especially if you aren't in calculus or you're just learning derivatives. But the definition of voltage is given right here, okay, where voltage is your electric field intensity integrated, that's what that little s is, over some distance. And an integration is essentially the opposite of a derivative, okay? So I'm not going to worry about it, but it's essentially kind of multiplied, but a little bit more complicated. And for a spherical source, we know that E is equal to K Q all over R squared times R, right, the integral of that. So that becomes K and Q, which are constant, right, when we're in a field, integral of 1 over R from some distance, let's say infinity, to some other distance, some R, okay? Now, you don't have to fully understand that, but I just want to see, when we get the final result, you can see kind of where it came from. Okay, again, V equals E integral R, which is similar to the equation we have for parallel plates where V equals E times D. So you can see kind of the similarity there, where again, with this integral sign is kind of like a multiplication. Okay, so if I substitute again what we know about E field and we apply this, we get the result, long story short, that voltage at any given point in space when you're in an electric field is equal to 1 over 4 pi epsilon naught, that's your K, times the field charge, which I'm going to denote with capital Q, divided by the distance. Not squared, simply the distance. So this equation looks remarkably like our E equation. In fact, if I write our E equation over here, I wouldn't write it. I would get E equals K, 1 over 4 pi epsilon naught, absolute value of Q all over R squared. So the note difference is the R squared versus the R, and this is a vector, whereas voltage is a scalar. Very, very important to remember that it's a scalar quantity. There's no direction associated with it, even though we're going to learn there is positives and negatives. Note that there's no absolute value here, so you have to put in a negative value if it's a negative field charge, and certainly a positive value if it's a positive field charge. Okay, so here's a situation. I've got some field charge Q, and I can choose some point in space, right? That is R away from it. So why do we care about the voltage? So there's some voltage at that point. Well, if I then bring in a test charge, a Q, to this point, little q, that's going to have potential energy. Because let's think about this, and again, maybe I won't draw. Let's say that Q started way out over there, where it's essentially at infinity. And then we brought it in. We don't really care how we brought it in. It could take in any path, and we got it there. Well, in bringing it from infinity to this spot, R away, we had to do work on it. And if we did work on it, we had to have changed its potential energy. And if Q is a negative test charge, then we're kind of going against the force. So it's almost like if if this is a positive test charge and it's a positive field charge, then it doesn't want to get closer, so we do work on it so the potential energy goes up. And if I let it go, then it's going to zoom out, and that potential energy is going to convert to kinetic energy. So we want to understand where this is coming from. All right, now how do we develop that equation for potential energy? Well, it's pretty straightforward. It directly comes from knowing what your potential is at that point. We already learned from a previous tutorial that potential energy, electrical potential energy, UE, is nothing more than the voltage you are at, position, multiplied by whatever charge you bring there, your Q, little q. Okay? So, like I said before, it's not the big Q that gives rise to potential energy per se. That's buried in the V. It's whatever little q we bring to some spot in the field. And if we use our equation for voltage from before, we can now express potential energy as a function of R. That's nothing more than 1 over 4 pi epsilon naught, excuse me, times Q times little q all over R. And again, this equation looks remarkably like Coulomb's law, where that would be F equals 1 over 4 pi epsilon naught times Q, but that would be over R squared. So we have 1, 2, 3, 4 equations that look very, very, very similar to our vectors and go by inverse square, to our scalar and just go by the inverse of R. All right, so let's do some practice problems with this, try to make this a little bit more concrete. So imagine our class static generator, where its radius is roughly 15 centimeters. And we've already learned that when we charge it up, it's on the order of microcoulombs. So let's assume that it's negative 5 microcoulombs. Okay? So we can ask ourselves, what is the electric potential at the surface of that? In other words, we are 0.15 meters away from the center. All right, I'm asking for electric potential. That's V, not U. U would be electric potential energy. And I can't answer that unless I know what charge I bring to that spot. So I'm solving for V. Since it's a spherical source, I would use the equation we just derived. And I'm just going to use the K, Q, all over R. Okay? K is 9E9 units. Q is the charge of the sphere that's giving rise to the field, so that's negative 5. Note that I have to put in a negative 5 in there, times 10 to the negative 6 coulombs. I won't bother with units. And divide it by the distance. I convert it to meters, 0.15 meters. I'm not squaring it. Okay, punch this out in a calculator. The negative is retained, and I get negative 300,000 volts. Or negative 300 kilovolts. That's a really, really large voltage. That's a huge amount of voltage just by that charge, and we are at the surface of the sphere. If we were to move another radius away, then we'd expect our voltage to be half that, 150,000 kilovolts, or excuse me, 150,000 volts, and so on. Okay, so again, we see that if we look at voltage versus R, it drops off inversely like we saw in our activity. Okay, now, energy. If voltage, you say, well, 300,000 volts, that sounds dangerous, danger high voltage. Why aren't we worried about that? Because it's not voltage that's the issue. What is the issue is energy. Okay, how much energy one gets transferred to somebody if they touch a high voltage source. So when you touch it, what's going to happen is charge is going to flow through you. And the charge is going to go, so the voltage is going to go from 300,000 volts to 0 volts when it discharges into you. So the amount of energy that gets transferred to you, I'm just going to call it U even though it's a potential, will be equal to whatever Q gets transferred times a change in potential. All right, or I should say change in this equals that. So how much charge moves through us when we discharge it? Well, all the charge that was on there. So negative 5 microcoulombs, okay, multiplied by 300,000 volts. All right, multiply those out, and I can do that for you. It's really negative 300,000 volts, so I'll get a positive energy as we'd expect, and we'll get 1.5 joules. All right, so even though we have a really, really high voltage, because we have a tiny amount of charge, we're going to get very little energy. So the lesson, high voltage is only dangerous when a lot of charge is involved. And that's not the case with static generators. Okay, with wires in your home, there's essentially infinite amount of charge that can be there. So that can be really dangerous. All right, now let's take this a little bit more detailed. So I've got our 5 microcoulomb charge here. That's our field charge, big Q. And now what we're going to do is we're going to bring in a test charge, a negative 1 microcoulomb test charge. And we're going to bring it from infinity, in other words, really far away, to a point 0.40 meters away. So from here to here is 0.40 meters, okay, and it started way out here at infinity. And we want to calculate, first of all, the change, that's important, in electric potential. In other words, we want to calculate delta V. Okay. So we have an equation for the voltage at this point. We need to have a calculation for voltage at that point, and we're essentially just subtracting them. The difference in potential, the change in potential. So I'm going to do this right below here. So that's going to be, so delta V, by definition, is going to be our final state of voltage minus our initial state of voltage. Our final state is nothing more than K, Q, all over 0.4. Right? We ended up there 0.4 meters away. We know what big Q is, and we can substitute it later. Minus, well, what was our initial state? Well, there's K. It's still Q from our field charge. We're just how far away? Infinitely far away. Okay? Now, hopefully you've learned some point in math that when you divide by zero, or excuse me, when you divide by infinity, that's essentially zero. So our final answer is going to be our change in potential is equal to 9E9, I'm not going to put in numbers, times, I will put in -5 microcoulombs, not convert that micro, all over 0.4. So this is similar to the problem we did earlier, except that rather than be right here at the surface, we are now at a point that's a little further away. So we expect the voltage at this point to be less than the 300,000 volts. It's still going to be negative. Okay, and if we punch out the numbers, we find that it is about 112,500 volts. Okay, so we're still at a very high voltage. Now we can ask, what was the test charge's potential energy at that point? Okay, so the potential energy at that point, UE, is nothing more than the voltage at that point multiplied by the amount of charge that I brought there. Okay, so we just figured out that our voltage at that point is negative 112,500 multiplied by -1, because it was a negative test charge, times 10 to the -6 coulombs, okay, and multiply that out, and we're going to find that our amount of energy is a positive 1.12 joules. So less than we had before when we brought it further in. I'm sorry, not 1.12, 0.112. I made a mistake there. I think I might have made a mistake in the previous one. It might have been 0.15 joules, but that's okay. All right, we'll do more practice with this. But again, if we can find voltage, what the potential is at any point in space using a general equation, and then we can find energy by multiplying a particular test charge by the voltage at that spot. Okay, lastly, in the last few minutes, let's look at inside a conductor. What's true of voltage? Okay, so if I've got a positive field charge right here, we know that the voltage field is going to be positive everywhere else, and it's going to drop off by the distance. How about inside? Okay, well, what do we already know? We already know that field intensity inside a conductor is always 0. So therefore, it would be tempting to think that the electric potential inside there would be 0. Okay, however, that would be inconsistent with the concept of work. All right, the idea of electric potential is tied with work. So let's follow me. And if it's inconsistent with that, then it will be inconsistent with the idea of potential energy and therefore difference in potential. So long story short, it's not going to be 0. So what is it going to be? Well, if E is 0 by definition, or it has to be, then to move a test charge from the surface to the interior. So if I have a test charge here and I move to the interior, if there's no E field, then there's no work done on it. There's no force that we have to overcome. And if there's no work, then the change in potential must be 0 as well. Therefore, the final potential must be equal to the initial potential. Okay, so if we're here at a certain voltage, V0 or VI, then it's got to be the same no matter where we are. So the electric field potential inside a conductor must remain constant. And that's consistent with the idea that the force field is 0 on the inside. No work has to be done. So if we look at this situation here where I have a charged sphere of radius r, and I want to look at voltage as a function of any r, I'll go over here and mark the radius. What we can say is at anywhere from here to the center, it's going to be a constant value. We'll just call it positive. You know, technically it's negative here because we have negative charges, but let's look at the absolute value. Then if I draw this, it's not an asymptote. It actually intersects here. Then it falls off inversely. But again, right here is not an asymptote. Whereas if it was E field, we would have to do that. Okay, so that sums up electric potential in general. A little bit more difficult than uniform field. We'll do practice with that. Comment with questions.